Okay, we're on day 2, and it's titled Dilations with Lines and Segments. And in our warm-up, we have determined the value of x and the measure of angle J. All right. We learned this theorem way back in Unit 3, that these two angles here are called non-adjacent interior angles, and that if you add them together, you will end up always equaling the exterior angle on the third angle of the triangle. All right, and so there's our equation. We're going to take 5x minus 3, add 4x minus 2, and that's going to equal 10x minus 20. We're going to combine our like terms on the left-hand side to get 9x minus 5 equal to a 10x minus 20. I'm going to go ahead and subtract the 9x so that we end up with negative 5 equals x minus 20. I'm going to go ahead and add 20, and we're going to end up with x equaling 15. And that's one of the questions that they asked for. Okay. Second question is they want to know the measure of angle J, and there's two ways we can do it. We can plug into the two angles in the triangle and use triangle sum, or we can plug into the exterior angle and use linear pair. I like to use both if I'm really checking myself, but if I'm not, and I'm only doing one of those two options, I usually go with the exterior angle, so I only have to plug in once. That exterior angle ends up being 130 degrees. And I know that two angles next to each other on a line with a separator in between them have to add up to 180 degrees. And so 180 take away the 130 is going to leave me with 50 degrees. Okay? And that is the measure of angle J. All right, so we are going to dilate, not triangles today, we're going to dilate lines and line segments. Okay? What we have to remember is that on a line or on a line segment that there are coordinates or points, and we're going to choose at least two of those points because it takes 2 points to make a line or a line segment, and we're going to apply the scale factor of our dilation to them. Once we have our new points, we can go ahead and graph them, and once they're graphed, we can connect them. Okay. If we have to ask about the equations of lines or line segments, remember that lines and line segments have two parts to them, a slope and a y-intercept. And if they're graphed, you can find both of those from your graph. Okay. There's also a little trick. When we dilate lines and line segments, our lines will always be parallel. And if two lines are parallel, that means they're slanted the same. That means that they have the same slope. So remember that slope will be the same since our dilated lines will always be parallel to each other. Okay. Our y-intercept, because it's a point, will always be multiplied by the scale factor. All right. So those are two things to remember. All right, so here's our first question. 1A says that segment PQ has endpoints and that P is at -3, 1, and that Q is at +3, +2. And there's our line segment PQ. They want us to graph segment PQ, which we already did, on the axes below and graph its image after a dilation from the origin with a scale factor of 3. Okay. So a dilation from the origin with a scale factor of 3. So because we're dilating from the origin, all we have to do is take our scale factor of 3 and multiply all x's and y's by 3. So go ahead, multiply by 3, multiply by 3, multiply by 3, multiply by 3. And now P prime is going to end up at -9, 3, and Q prime will end up at 9, 6. And now we can go ahead and graph them. So -9, +3, and that's P prime. And then Q prime is at +9, +6. So take a look. Every single time it's going to happen with dilations, okay, is that they're going to end up being parallel to each other, which means that they're tilted the same, which means their slope is the same. Okay. All right, part B says, is a dilated segment still a segment? Yes. Part C, what is the relationship between PQ and its image after the dilation? They are parallel to each other. Okay, that's one thing. There's a second thing, okay, that if I were to measure the length of PQ, it would fit into P prime Q prime not only one time, a second time, but a third time, because your scale factor was 3. So we can go ahead and say that the image is 3 times as long. Okay, and there's one more thing. Okay, notice your center of dilation was the origin. Okay, in that our line segments, take a look. Here's the distance from P, from the origin to P, and then this is the distance there. So notice it's 1, 2, 3 times as far away from the origin. Okay, so we can say that the image is 3 times farther away. The image is 3 times farther away from the center of dilation, which is the origin. All right, so there's 3 things that happen there. Okay, let's take a look at number 2. In number 2a, it says graph the line y equals x plus 2. So we have graphing calculators, and anytime the equation's in y equals, we could type it in and go to the table, get some points and copy it down, and then we could graph our line that way. All right. So that's if you forget or don't know how to graph a line. If you know how to graph a line by hand, you don't need the calculator. That's also helpful. All lines have what they call a slope and a y-intercept, and they use the letters m and b. If you remember, y equals mx plus b, so you know where to find the m and the b. Okay, b is usually a number added or subtracted right to the end, which is a positive 2. And remember that this is my y-intercept. In y-intercept, I always used to say b is where you begin. So you begin on the y-axis at 2. Okay, so that's always my first point that I plot. Your slope is found as the number in front of the x, and in this case, there is no number, so we take it as a 1. 1x is the same thing as x, and so our slope is 1. I like to think of it as my slope as a fraction, and so if I make 1 into a fraction, for instance, 1 over 1 is the same as 1, but now it's a fraction. Slope is also known as rise over run, so the top number 1 is my rise, and the bottom number 1 is my run, and because it's positive, 1, I go up from my rise, and positive 1 on the bottom, which means I run to the right 1. All right, so if I go up 1 over 1, rise 1, run 1 to the right and up, okay, I get a bunch more points. Okay, and then I could go the other way as well, and that's going to give me my line. All right, if you have a straight edge, I suggest using it to get your nice picture. I don't have a straight edge on here, so I'll try my best to make it neat. Part B says dilate the line with a scale factor of 2. So remember, all you have to do is take 2 coordinates off of that graph and multiply them by 2 and plot them, and you'll get your new line. Okay? I totally suggest using your y-intercept if possible, and the coordinates of that y-intercept are 0, 2. And if I multiply them by a scale factor of 2, it's going to change it to 0, 4. And that's actually my new y-intercept. Okay, so I'll plot it. And then I just need one more point. Okay, you don't want to pick something too far away either, because if you multiply by 2, it might end up off your graph. So you might want to pick something that will fit. All right, so maybe like this point here has coordinates of 2, 4. I know that if I multiply 2 and 4, that should still fit on my graph, because I should get 4, 8, and that will fit. So if I graph 4, 8, 1, 2, 3, 4, 8, I get that point. And you could dilate more than 2 points if you want a more accurate line. Okay? But if I go ahead and connect those 2 points with a straight edge, you're going to realize the same thing happened in the last one, that your original and your new one end up being parallel. Okay? All right, so part C says, what is the equation of this line? Well, Again, equations of line depend on two things, your slope, which is known as m, and your b, which is known as your y-intercept. So our y-intercept is now 0, 4, or also known as just the 4. Okay, all y-intercepts have an x-coordinate of 0, so we don't need the 0. Our slope, notice our lines are tilted the same, therefore their slopes are the same. So what we do is we go back up and say, hey, I'm going to steal your slope, which is 1. And so now my equation of my line is y equals 1x, or just x, plus 4, instead of my original, who was y equals x plus 2. Okay, so you usually just keep the same first part of the equation. The y equals always stays the same for all equations. Okay, because the slope stays the same. The 1x that we originally had stays the same. And then our y-intercept gets multiplied by the scale factor. Okay. Part D says, is a dilated line still a line? And the answer is yes. And part E says, what is the relationship between the line and its image after the dilation? So let's see if we can say the same three things that we said in the last one. Are they parallel to each other? And the answer is yes. So we'll say they are parallel to each other. The second one says that the image is 3 times as long. Well, we cannot say that. Number one, it wouldn't be 3 like it was in the last one. It would be 2. But because these are lines and lines go on forever, you can't measure the length of it, if you noticed, okay? So we cannot say the same thing we said about this one. We can't talk about the length of it because these are lines instead of line segments. So what about the last one? In the last one, we said that the image is 3 times farther away from the origin. We can't say 3, but we can say 2 times. If you notice, like from the distance from our y-intercept from the origin, and then our new y-intercept to the origin, notice that distance is twice as long. So we can say that the image is 2 times, because our scale factor is 2, farther away from the center of dilation, which, remember, our center of dilation is the origin. Okay. All right. I will see you guys on the back side for the rest of our notes.